Good morning, good afternoon, and good evening, everyone. Thanks for starting off your week with us for another Data Engineers Lunch. This afternoon, it's going to be Data Engineers Lunch 95. We are quickly approaching episode 100. We'll talk about that a little bit later. This afternoon, we have special guest Obi going over Python parallel processing frameworks again. We do apologize. We had tried to have this topic covered a few weeks ago, but ran into some technical issues. I'd like to thank everybody that was with us then and joined us again today. I'd like to thank everybody joining us again for the first time. We're really excited about this topic. So just a few housekeeping items. The host for this event are Raul and myself. I'm Akwi Wahiri. If it's your first time joining us, we are looking for speakers and sponsors for this event. If you're interested in either opportunity, please reach out to me at akwi@anant.us. We are a part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is made up of a lot of different groups, all generally surrounding data. You can find out more about those groups at the addresses listed below. So what do we cover here at our Data Engineers Lunch? If it's your first time joining us, we cover everything about data. We cover everything from the ingress and egress of data and everything in between. We cover everything from databases, ETL, data wrangling, and all the tools and processes in the data engineering world. We do want this to be an inclusive experience, an inclusive community for everyone. If there's some topics you'd like us to cover or something we've covered in the past you'd like us to revisit maybe in more detail, go ahead and leave us some comments. If you prefer to shoot me something a little bit more private, go ahead and send me an email at akwi@anant.us. We really are open to hearing from you. Group rules, if you have a question, go ahead and ask it. As I mentioned earlier, please be polite and courteous to everyone. And we do want this to be a community, so share what you know with us. Here at Anant, we build and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. We'd like to thank our program sponsors listed below and also our organizational sponsors. Quick 15-second announcements. If you have any jobs, meetups, hackathons, conferences, classes, please go ahead and leave them in the chat with a link and a short description of what everyone can expect. Events we have coming up. Obviously, we have our Data Engineers launches on Wednesdays, our Cassandra launches on Thursdays. If you haven't already, please join our meetup groups, or you could subscribe, or you could just check out our events page, bookmark that, check it frequently, and or you could subscribe to our YouTube channel so you get notified directly when we go live. Our runbook is available using Terraform and Ansible to install Cassandra on AWS and Azure. Please download your copy if you haven't already. This copy is free. I'll go ahead and leave a link to that in the chat. And I think that's it for me in terms of housekeeping items. I'll go ahead and hand it over to our speaker this afternoon. Over to you, Obi.
All right, thanks, Akwi. Let me just get set up. As you heard, my name is Obioma Anomnachi, and I'm in charge of Data Engineers Lunch for today. I generally prefer to take questions during breaks. Akwi will handle getting those to me. Today's topic is parallel processing in Python. We're going to talk about a bunch of different methods for doing this. So starting out, why would you want to do parallel computing? Or what even is it, I guess? So parallel computing is a type of computation where many calculations or processes are happening simultaneously. You take your large problems and you cut them up into small pieces, and those smaller ones can all be solved at the same time and recombined to get you your output. It's very useful for high performance computing, especially since Moore's law has sort of fallen off recently. You can no longer frequency scale your computer chips. Like basically computers aren't getting faster very much anymore in terms of, clock speeds, but high amounts of parallel computing can maintain that sort of trend line. In Python, there are several methods of parallel computation that we're going to talk about. Multiprocessing and threading are both Python libraries, inbuilt Python libraries that divide the workload across threads or processes, depending on which one you're using. Coroutines and concurrent, coroutines is another Python library for concurrency, which is very similar to parallelism. Concurrent futures is sort of a wrapper library for those first three. And then worker distribution frameworks are methods of parallel computing that take that work on multiple machines instead of just one machine. So starting off with multiprocessing. So if you look at the diagram here, there is the main process that's managing everything, and then it spawns processes 1, 2, and 3 with their own CPU and memory. You can execute your parallel code on multiple CPUs or multiple cores within the same CPU, and it achieves parallelism by creating separate processes that each have their own memory space and Python interpreter. That's going to be different from when we look at threading, basically in how it relates to the Python interpreter. Each process has its own memory, but you can communicate using IPC between processes using like pipes and queues and stuff. It uses a process object to represent a single one of those processes, and you can start it using the start method and join into it using the join method in order to have your main program run along the lifetime of that process. Processes can share data between each other. You can use the multiprocessing queue, pipe, or value classes to pass data in between your processes. And the multiprocessing manager class can be used as a shared namespace to create a shared namespace between processes, allowing them to share basically arbitrary Python objects, complex data structures in between them. Multiprocessing pool class can create a pool of worker processes which execute a function on multiple inputs in parallel. And it's not always suitable. Well, we'll see this with all of the methods, essentially. They're not suitable for every task. This one, multiprocessing in particular, is not suitable for IO-bound tasks because of the overhead of creating and managing the processes. So threading is a separate Python library for multiprocessing. It allows for thread-based parallelism all within the same process. Threads are lighter weight than processes, and therefore they're more efficient in certain cases. They have less overhead to create and manage. You can use threading for a variety of tasks, improving the responsiveness of a GUI application or parallelizing IO-bound operations. So where multiprocessing was not good for things that are bound by IO, like say reading in data from external systems, whether that's the internet or whether that's a disk drive. If you have to constantly read in, if you're doing IO constantly, and that's what's binding the actual processing, you're going to waste a lot of time if you're using multiprocessing to generate threads to do that ingestion, whereas threading is a more efficient way to do that. It's not exactly the best choice for CPU-bound tasks because of the global interpreter lock, which can limit your true parallelism. Basically, the way that this works is that all of the Python interpreters on a single machine are sharing a pool of potential threads. So if you have other processes running on your machine, then GIL can essentially lock your new processes out of getting access to enough threads to truly run in parallel or to make full use of their parallelism. There's actually a fix coming for that in, I think, Python 3.12, 3.14, something like that, that basically each interpreter is going to have their own GIL. So all of your Python programs, each running in their own interpreter, will have their own pool of potential threads that they can work with. The threading library, just like the multiprocessing library, provides a whole bunch of classes and functions for working with threads. Thread class is the main one used to create and manage individual threads. The lock class can be used to synchronize access to resources between threads. Threading has the potential for race conditions and other synchronization issues when you're creating or when you're having multiple threads running at once. And it can also be used in combination with other parallel computing libraries, including multiprocessing, or ones we're going to talk about later, to achieve more complex forms of parallelism. So your multiple processes, if you're using multiprocessing, can each spawn multiple threads themselves. Coroutines. So coroutines are specifically made to work with IO-bound operations. They're using the same pool of resources, but restricting access to these based on these individual requests, based on when they return. So you're doing asynchronous programming with coroutines. There's one thread of execution, but there are multiple tasks. Async.io is the Python library for it. Uses coroutines and event loops. Define coroutines that are executed concurrently, and then run them using the event loop. There are several built-in modules, just like the other two we talked about. Async.io Stream Reader and Stream Writer classes are used to interact with network socket files and IO sources of any kind in an asynchronous manner, which means that the processing of that, basically the resources that would be used to run that thread, are suspended or allocated to other tasks until you get your data back from your request. So you can see on the chart over on the bottom right, you have the CPU processing time, which starts, it sends out request 1. Whatever resources were going towards request 1 are now put towards request 2, sends out request 2. All those resources are now put towards request 3, sends out request 3. And now, since all 3 of them are waiting, there's no CPU utilization happening in that time in the middle. And then request 1 comes back and you can continue processing. Request 2 comes back and you can continue processing. Request 3 comes back and you can continue processing. One important consideration if you're using async.io or coroutines is the potential for blocking operations to interfere with the event loop. So if there's an operation that's taking place, it's possible that the event loop won't be able to shift any resources. Concurrent Futures is a Python library that provides you a high-level interface for working with parallelism and concurrency. So essentially, you define your tasks, and the pool executor manages the parallelism or concurrency of those for you by splitting them up into threads and processes without direct intervention from you. So tasks are submitted to the executor as callables. You just pass in your function or your method. And there are 2 implementations of the executor interface: thread pool executor and process pool executor. And the executor will schedule your tasks to run asynchronously and return future objects that can be used to track the status of them. Basically, the advantage of concurrent futures is that it's easy to use. It abstracts away many of the details that you would previously need to know to use threads or multiprocessing. But one drawback is that you don't have as much fine-grained control over the parallelism. Like I mentioned earlier, you could use threading and multiprocessing together to achieve higher levels of parallelism than using either alone, but concurrent futures doesn't really allow you to do that. And then worker-based distribution. So we kind of talk about that a lot here at Data Engineers Lunch. You use distributed computing frameworks like PySpark or Dask, which provide a way to scale up parallel processing across multiple machines. Generally, they will use a master worker architecture where the master node coordinates the work and the worker nodes do the work, actually perform the computations. So what we have at the bottom here is sort of a diagram of a Spark cluster where there's a driver program, and the Spark context there communicates the cluster manager with individual worker nodes, which have executors, they have data, and they have individual tasks to complete. And all of these parts are interconnected. Your data comes in, gets partitioned and distributed across the worker nodes, which allows for parallel processing large data sets because it's happening on different machines with their own storage capacity. So PySpark and Dask both provide high-level APIs for working with distributed data, and they abstract away many of the details of it, just like sort of concurrent futures does, where you don't have to understand too much about the underlying system. You can say, just like you could say the pool in your concurrent futures is managing the lower level distribution of your processes. You could say that the cluster topology essentially is abstracting away many of the details of your actual sort of data distribution and parallel processing and all that kind of stuff. And a lot of worker-based distribution systems have fault tolerance and automatic recovery from worker node failures, ensuring that the computation can complete even in the face of unreliable hardware. All right, we're going to be moving on to the demo in a little bit, so this is a good time for any questions. All right, no questions so far. So we're using Gitpod for our demo today. We're going to be working with a bunch of these different parallelism options and giving them the same test to see sort of how they perform and how they're used differently. So the first thing is, well, first Gitpod installs the requirements. The ones we're adding are LXML for Beautiful Soup. Beautiful Soup for parsing HTML, and then Dask as our worker-based distribution strategy that we're using today. Dask is it's basically a bunch of different data sets and types that do specific processing really well, parallelized. And so the idea is that you would use a Dask cluster to do a lot of, basically, if you have NumPy data sets or things like that, Dask will provide you with their own implementation, essentially, of those processes that work in a parallel manner and are optimized for doing that kind of computation. What we're going to use it for today is kind of not the main purpose of it. Like I said, it's meant for doing mathematical operations in a parallel manner, but the test that we're actually going to give it today is web scraping. Okay. So the first thing we need to run, is this visible, by the way?
Yep, looks good, Obi.
Okay, so the first thing we're going to do, the task that we're actually giving all of these is to scrape a bunch of links from Wikipedia and then give us back all the links that are embedded in those pages. So the first thing that we do is that we go to Wikipedia main page and we extract all the links there for our list of links that we're passing in. Okay, we run this, and rather than saving everything into an actual file in human readable format or something like that, I pickled it and stored it. So it's the actual Python object of the list that's serialized and stored inside this pickle file. And all of our other files, I'm going to load that in, unpickle it, and start working. So step one, no parallelism. So this is our first code. What it does is it loads in the object, starts the timer, goes through every URL in this every URL in the list, gets the results, passes them to Beautiful Soup's parser, and extracts the title for every page in the HTML results. And then it puts that into a dict with the original URLs and presents it to us. Ends the timer and then prints it out, as well as how long it took. All right. So we got back our dict, all of the URLs and their associated titles. And then the last time took 17 seconds. So let's see if we can speed this up. So first is thread parallel. I guess maybe we should go in the order of the presentation. So first we're going to do multiprocessing. So if you remember, multiprocessing is the one that spawns a process for each parallel I don't want to say process again. Anyway, it spawns processes for each task. And you can see what we're doing here is we are starting a pool up to whatever the CPU core count is on this machine. We get our results. And then we pass them through that same parsing process and print them out in the same way. So why is the GUI so uncooperative? Oh, a question. What's an example of an IO heavy task like those you described in a few sections? So this actually can be one. So depending on how long it actually takes to get your results, if you were waiting for a couple of minutes rather than, a couple milliseconds here. And you might even be able to see it as we go on, depending on which method of parallelism we're using, we get slower and faster times. But basically, if there's any period where you're waiting on IO, having your process or even your thread running, taking up resources while still waiting for that stuff to respond. Or say if you need to process files in batches that take a little while to download each one, if you have to download them during the process rather than download them before, that's the type of thing that could be an IO bound on your multiprocessing. Okay, so in this case, we're down with multiprocessing from 17 seconds to 12 seconds. And then we can look at threads. So here, we're using threading.thread and passing it in a Lambda function that gets the page from the URL. And then we are combining everything into a dictionary. So previously we used zip because they were in the exact same order, in the exact same, the results were returned in the same order as the URLs. That's not necessarily true this time, but we're using, or both in list format, both the exact same length. Basically, there are things that made it possible to use zip before where it's not quite possible now. But we're doing the same process, start the timer, get the URLs, pull the pages, extract the titles, etc. Yeah, but basically the important part of IO heavy tasks is that you are waiting for results to come back. So in this case, threads, we got 14. So the difference here, these are not actually directly comparable. They're using the same list, but the threading and the processing actually get different amount of resources here because we create processes with our processes bounded by the number of CPU cores, but we create a single thread for each URL here. So those two aren't directly comparable, but still the elapsed time is 14 seconds here. And then we want to say async IO. So what we're doing here is we're defining asynchronous functions like fetch title, which take a URL, pull the response, and then extract the title and give it to us. And then we're defining our main function, and because it uses an async function here, this is also async def. But essentially it works the same way. You create all your async IO tasks here, and then you gather them here. You use await async IO gather all your tasks in order to get back the data that they give you, and just wait until all of them have returned. And then we can use zip again to put them all back. Oops. This one that was already part of the requirements. Try that again. Okay, so like we said, async IO is very specifically for doing this sort of concurrency where you're limited by IO. And so this time we got a much lower elapsed time, 7 seconds total for the same task. So making sure that you're picking the right one can actually have a huge effect on how fast your code actually runs. And then concurrent futures, when we look at the code here, basically it's all abstracted down into here. So we create our executor, third pool executor, and then we get all our title futures here, and we wait until we get the results in here. So it's a very efficient way. We don't have to mess around with, how many parallel processes should we spawn, and we don't have to write any Lambda functions or anything like that. We just write a function, and we pass the Python callable in here with all of the things it's supposed to act on. So it's simple to use and manage, but it doesn't actually really get us much time improvement over using parallelism or threads by themselves. But we are still down from not using parallelism at all. So you get the advantages of parallelism, it's easy to use, but you don't necessarily get any improvement over those individual types of parallelism themselves. It might not even choose the best form. Specifically because it's limited to either threads or processes. So if async IO is the best, then you're not getting that performance out of concurrent futures by itself. And lastly, Dask. So we import all the Dask stuff. So what we do here is we have our own download URLs. Function where it starts the time. It uses this DB, so that's our Dask bag from sequence URLs. So it turns our list of URLs into a Dask object and returns mapping each item in that bag to download URL, which is this function here. Basically, it's the same one we've been using, request.get, beautiful soup to parse out the title, and then strip out any extra characters here or return an error. So we map, we hit .compute, and then we return the elapsed time. So just like before, all we are doing is opening up the loaded pickle file, putting all the URLs into our task, and then printing out the results. So even though the start time and end time are inside the function here, they're placed basically at the exact same as they would have in these other Python files. So when we run it using Dask, (8.2 seconds. So in testing, this Dask task was even faster. At least during local testing, this Dask task was even faster than the async IO parallelism. But we're getting performance basically on par with our best manual parallelism by basically just handing it off to Dask. There is another question. Is there a trade-off to be made between parallel operations and database performance? You say that parallelism large operations has a standard impact or a database, or does it depend? So I think it does depend, especially on what types of overhead there are for things like reads or inserts from your database. So if a non-parallel process could load a large proportion of data from your database in a single read, or push that data to your database in a single batch, and that was the performant way to use that database, versus on the other end, something where a database where it's easy to do a whole bunch of reads and a whole bunch of writes, you could get even more performance, like just on the IO side, by talking to your database in that way. All right, that is it for the demo I had prepared. So if there are any more questions, otherwise I will be passing it back to Akwi to close out.
Thank you, Obi. Let's go ahead and give the chat a few more minutes. If you have any questions for Obi, please go ahead and drop them in the chat. If you've liked this video or any of our previous videos, please make sure you like it, subscribe to the channel as well. This week, we do have episode 5 of our Automate Your Job with Chat GPT series coming up. I believe that's going to be episode 5 this Wednesday at 1 o'clock. If you haven't already, please do subscribe to the channel and keep an eye on our events page. That is Anant.us/events. And just a bunch of thank yous in the chat, Obi. Again, I'd like to thank you as well for another great presentation. I thank everybody for joining us live. Thank people who are watching this a little bit later. We appreciate you guys. Please do subscribe to the channel. We have something special in the works for the 100th episode. We hope to start making these lunches in person. Just keep an eye on the meetup group. We'll leave any updates there. And we are planning on something special for the 100th episode. If you have any ideas, any suggestions, again, please don't hesitate to reach out to me at akwi@anant.us. And it looks like there are no further questions. So again, Obi, I'd like to thank you. I'd like to thank everybody for joining, and we'll see everyone same time, same place next week. Thanks, everyone. Take it easy.